Thank you. So I'm Marika Swanberg, and I'm happy to present this joint work with Sam Haney and Damien Desfontaines. All right, so let's say you're doing a user study, for example, and you want to publish user search queries. A naive way of doing this would be to just output the union of all these queries. But clearly, queries can be quite revealing, and AOL actually found this out the hard way in 2006. So what we might want to do is take a more principled approach and use differential privacy to give us some privacy guarantees in this space. So this problem is called differentially private partition selection, also called key selection or set union, depending on who you ask. And the basic setup is that each user has a set of potentially multiple items, and you want to output a subset of the union of those items while satisfying differential privacy. And we want this subset to be as large as possible, so we'll measure accuracy in terms of the size of the output. All right, so beyond publishing search queries, this has lots of applications. For example, vocabulary extraction, or if you're studying frequencies of rare diseases, or really anything where you're aggregating over groups where the groups themselves are private. So it's sort of a foundational building block for many types of statistical analyses. So within this space, for the special setting where each user has exactly one item, Desfontaines et al. Found an algorithm that has an optimal privacy and accuracy trade-off. But in our setting where users may have many items, there's kind of two classes of algorithms in this space. The first are these stable histogram type algorithms that are highly parallelizable, and they work well on industry-sized data sets, but they tend to have lower accuracy than this other type of algorithm, these greedy partition selection algorithms that have really high accuracy, but inherently just can't be parallelized. So you can't kind of run it on a large cluster. Yeah. Okay, so our research question is, can we design an algorithm that achieves both high accuracy and also is parallelizable so that it's suitable for industry purposes? The answer is yes. We designed this algorithm called SIPS, which does have state-of-the-art accuracy. It's massively parallelizable by design. And in this work, we also give a thorough empirical evaluation of existing algorithms, both in terms of running time and accuracy. So let's talk about just a generic partition selection algorithm. It has three basic steps. First, you build a histogram over the user items. So for example, the bins might be queries or words. You then add a calibrated noise, maybe Gaussian noise, to each count, and then return items that have noisy counts above some specified threshold. And so the noise you add and the threshold will be determined by your privacy parameters, and in general, higher threshold gives higher privacy. All right, so so this is the basic format that all the prior work follows, and these greedy algorithms get better accuracy by processing users one by one and allowing users to update the histogram depending on the current state of the histogram. So they get better accuracy this way, but unfortunately, just by design, it can't, step one can't run in parallel for these greedy algorithms. So we do something a little bit different. We have these same three basic steps, but we take an iterative approach in our algorithm. So after, in step 3, we've returned a set of items to be released. We actually remove those items from the user's data sets and repeat the same algorithm on this smaller data set. And we divide our privacy budget across these 3 runs. Okay, so the way that we build our histogram is similar to this stable histogram style algorithm. So what we do is each user will truncate their set to some bounded number of items. And then for each item that remains in their set, they'll increment the histogram by 1 over the number of items that they have squared. And this part is sort of important for understanding how we get accuracy gains. So I'll explain that next. So let's say we have a truncation bound of 10 items, and our user has 4 items. This user will add 1 over 4 squared to each of the 4 items within the histogram, and will then follow steps 2 and 3 to return items A and B, let's say. In the next step, the user removes items A and B from their data set, so they now only have 2 items left, which means they can add 1 over 2 squared to each of these 2 items. And so what I've depicted here is the counts from the previous run, but actually the counts go up in the second iteration because users can add more to each of the items that remain. Their set of items is smaller. So the true counts get inflated on each iteration. Okay, and then in the very end, the user just has, let's say, 1 item left, so they can add a total of 1 to their the remaining item. Okay, so, and I should note that each of these individual steps is massively parallelizable. The iterations have to run in sequence, but we only do 3 of them. So it's not too bad in terms of running time. Okay, so there are 2 key ways that this algorithm boosts accuracy over just the naive approach. The first is that we're removing the previously returned items from user sets, which means that the user's counts can go up as the iterations proceed. And the second is that the way that we allocate the privacy budget among the rounds, we actually use a very small amount of budget in the beginning and then use more budget to discover kind of the tail end of this distribution. And so basically the threshold and the noise are decreasing throughout the iterations at the same time that the counts are increasing. And so these 2 actions together increase the number of partitions that we can return. Okay, so let's look at some results. Here's, I've plotted accuracy versus epsilon on the left for a fixed delta on a Reddit data set. And the SIPS algorithm is in pink here. And you can see that the accuracy is pretty much on par with the other, the 2 greedy algorithms that exist, while the accuracy of SIPS is about double that of weighted Gaussian, which was this one that scales well to industrial applications. And the same trend holds if we fix epsilon and vary delta. And in general, this trend holds across the data sets that we tried. Now what about scalability? So we created this synthetic data set with 80 million users and plotted the running time as a function of the size of the input and found that the 2 greedy algorithms timed out after 2 million and 10 million users, respectively. So they weren't well suited to these really large data sets, whereas the running time of SIPS has about the same, or not too much worse of a running time compared to weighted Gaussian. And this is on a very large cluster. Okay, additionally, we can fix the data set size and look at what happens when we increase the size of the cluster. So on the left, we have the running time as a function of the number of cores, the number of nodes within the cluster. And we find that SIPS's running time decreases as we increase the size of the cluster because it can really take advantage of this parallelism, whereas the 2 greedy algorithms up top the running time doesn't meaningfully change because they have to take this kind of iterative approach in building the histogram. And we can also do is fix the number of machines within the cluster, but increase the computational power of each individual machine. So on the right, that's what we've plotted, and we find that, again, SIPS's running time goes down But these kind of greedy algorithms, running time stays the same, even though you're increasing the amount of memory and kind of compute power of the machines within the cluster. All right, so just to summarize, we developed this algorithm that takes an iterative approach to partition selection. It achieves a trade-off between having state-of-the-art accuracy while also being massively parallelizable in its design. And we also provide this thorough evaluation of existing algorithms. And in the future, it would be amazing if we could get some analytical accuracy guarantees for really like any of these partition selection algorithms. Within our setting, no such analysis has been done. And then even more kind of pie in the sky would be to find an algorithm that has an optimal privacy and accuracy trade-off within this setting. That's all that I have, but thanks for listening, and I'm happy to take any questions.
Thank you. We already have some questions on the Zulipub. One from Valentin. He's asking, was this work motivated by real-world use case at Tumult?
Oh, at Tumult specifically? Yeah, so there are settings where, like, for example, if you don't know necessarily if you're doing a group by query, you're grouping over some attribute and you don't know what those attributes are. You don't want the user of your platform to have to like pass in the keys that you are grouping over. Instead, you want your framework to discover what those keys are. So that's one setting, just kind of convenience, but also like real privacy issues. So for example, search queries, your queries are potentially very revealing, and you would want to only kind of release queries that are popular enough that, that it won't like impact your privacy.
Thank you. We have a second question from Sundar. He's saying, since you need to build a histogram over all elements in the domain, does that mean that the domain of elements needs to be tractable for your algorithm to work?
Good question. So it's not all elements in the domain. It's just a histogram over all elements that appear in your data set. So this algorithm works even if the domain is unbounded, for example, which in a lot of settings, it's either unbounded or not easily numerable.
Another question from Minsin. Are there any general post-processing techniques that can be used to improve the accuracy of your algorithm?
Not that I know of, because so you just get a set of items in the output. So I'm not sure what you would do to post-process, but certainly that's a question you could look into.
Any other question? If not, let's thank the speaker and conclude the session.